In the last video, we talked about relative extreme values, relative extrema, and critical points. And what we said is that if we look at the set of all critical points, all right, among the critical points, all right, are the set of x values for relative extrema. But some of the critical points were not x values of relative extrema. And so what we have to do, once we find the critical values, we have to sort through them and decide whether or not they are actually a relative, are located relative maximum or relative minimum. And we have one means of doing that is that was what we call the second derivative test. Okay, so let's talk about that. All right, here's the statement of the second derivative test. Suppose that f is twice differentiable. That means you can take its first derivative and second derivative and evaluate them at x0. Then if f of x0 is 0, so we have a critical point at x0, and if f double prime of x0 is greater than 0, then f has a relative minimum at x0. If the first derivative is 0 at x0, again we have a critical point, and the second derivative is less than 0, is negative, all right, then f has a relative maximum. All right, and if the first derivative is 0 and the second derivative is also 0 at x0, then we can't tell anything. We'll have to try another way of determining whether that x0 locates a relative maximum or minimum. We don't know that it does, and we don't know that it doesn't. One thing maybe I should say is that your book also defines what's called a stationary point. And a stationary point is the critical, or the stationary points, maybe I should say, are the critical points where f prime of x0 is equal to 0. So notice in this case we're only dealing with those kinds. We're not dealing with critical points where the first derivative is undefined. We're only dealing with critical points that are stationary points. All right, let's take a look at an example here. Okay, so in this case we have f of x is equal to 3x to the fourth plus 4x to the third minus 36x squared minus 50. Okay, and let's calculate the first derivative. Maybe I should outline this. So the first thing we're going to do is we're going to find the critical points. So those are where the first derivative is 0 or the first derivative is undefined. So we'll have to find the first derivative. The first derivative here will be 12x to the third plus 12x squared minus 72x. And this, if you look at it, is a polynomial. It's never going to be undefined. So let's try and figure out where it's going to be 0. So if I look at this, I can factor it. I can factor out a 12x, and I'll have that this is equal to 12x times the quantity x squared plus x, all right, make sure I did this right, minus 6. And this I can factor further. This will be 12x times x plus 3 times x minus 2. Let me double check that I've done this right. X times x squared. 3x minus 2x is x in there. Yes, okay. So then remember our critical points here were where this is going to be 0. So let's set this to 0. And obviously it's going to be 0 when x is 0. When x is negative 3, and when x is 2. So these are going to be the critical points or we had called these stationary points because they make the first derivative 0. All right, now the question is, these are critical points, but do they locate relative extremum? Well, all right, to find out if they locate relative extremum, let's take a look at the second derivative. Okay, so the second derivative is going to be 36x squared plus 24x minus 72. And now if we just look at the value of the second derivative at each of these points, so look at the second derivative evaluated at 0, that's easy. Second derivative evaluated at 0 is going to be 0 plus 0 minus 72. Notice in this case, all right, since the second derivative is negative, all right, we have a relative maximum. And again, here's the picture. All right, the first derivative at 0 is 0. Okay, so we have a horizontal tangent. The second derivative is negative, so the function is opening downward. So if we have a horizontal tangent and the function is opening downward, we have to have a relative maximum. So x equals 0 locates a relative maximum. Another way of saying that is that f evaluated at 0 is a relative maximum. Okay, I believe in the next, I have these all ironed out here. Notice here I have the -3, 0, and 2, and remember those all made the first derivative 0. All right, the -3 makes the second derivative 180, which is greater than 0. So we have a relative min at x is equal to -3. We already saw a relative max at 0. And notice, because the second derivative was negative, here the second derivative is positive at 2. So we have a relative min. Again, notice at -3 and 2, all right, the second derivative is positive, so we're concave up. Let's take a look at this. So at x is equal to -3, notice we have a horizontal tangent because the first derivative is 0. The second derivative is positive, so we're opening it upward, so we have a relative minimum there. At 0, the first derivative is 0. All right, we have a horizontal tangent, but we're opening downward. The second derivative is negative, so we have a relative maximum. And at 2, we have a horizontal tangent. The first derivative is 0. The second derivative is positive, so we're opening upward, so we have a relative minimum again. But now let's see, what are the relative minimum? So the relative minimum, I'll have to list these on the side. The relative minima are going to be f of -3, which is -239, and f of 2, which is -114. Again, remember we said that the relative minimum was the height at the bottom of a valley. So the -239, all right, is how high we are. -239 is how high we are at the bottom of this valley, and -114 is how high we are at the bottom of this valley. The relative max is f of 0, which is -50. Remember, the relative max is the height of the top of this hill, and that height is a -50.